So I'm going to start with basically this overview and capabilities. This is so I'm presenting, but this is also work from a lot of stakeholders from the Coronagraphs working group, now called coordination team at STSCI, but also from external stakeholders. For example, for NIRCam, my counterpart is Jaron Leisenring in Arizona, or was at least. Some people from the, let's say, the instrument teams, NIRCam and MIRI. A lot of people, chronograph experts are in Paris for MIRI, but not only. So, and of course, the early release science team led by Sasha Hinckley, and basically yielded a lot of the things that we are talking about, and the results and the contrast curves we're going to show today. So to step back a little bit, there are basically 9 coronagraphs inside on board JWST. 5 focal plane masks are in NIRCam, and those are this one. I think you can see my pointer. There are actually more on the B module, but we don't use this one. We only use the A module for NIRCam. And I will give some more details after, but you can already see they seem to be outside of the field of view image onto the detector. And in fact, there's a trick for NIRCam to basically re-image that part, basically shift the field of view down so that the coronagraphs are seen by the detector. For MIRI, so MIRI is here with respect to NIRCam. MIRI is a bit different. The coronagraphs always see light if you want. They're always on the detector, but basically this is the imaging part of the detector, and the coronagraph are on the side. And each coronagraph, each focal plane mask is bound to a filter. So this is simulations from Marshall Perrin using WebPSF, which, by the way, now it's called STPSF, but a lot of people know it as WebPSF. So this is all simulations pre-launch, but that's basically what we expected. But it's still a nice view, because you see basically the inner working angle that you can achieve, from short to long wavelengths with NIRCam, and from short to long wavelengths with MIRI. The MIRI chronograph are a little bit more modern and aggressive in a way. So they are 4-quadrant phase masks, phase coronagraphs. And so they are designed to basically reach almost 1 lambda over D inner working angle, whereas the NIRCam chronograph the design is less aggressive and more forgiving in a way. And so it's designed to reach 4 to 6 lambda over D inner working angle. So we define the inner working angle here as the location from the mask center where you have 50% throughput. Another thing that you can notice here is the Leo stop. So in the pupil plane, this is basically an optical element, a mask in the pupil plane that will basically get rid of all the light that will, once it's in the focal plane, reduce your contrast. So this is kind of to get rid of all the, and you can see the way it's been designed is to avoid the segment gaps and also the spiders of the secondary mirror. And this is the Leo stop for the round masks, and this is the Leo stop for the bar or wedge masks, this is the focal plane, and this is the pupil plane. For MIRI, so as you can see, for NIRCam, we are not exploiting the full 6.5 meter diameter of the telescope. Unfortunately, it's equivalent to having a 5.2 meter telescope, and that's actually quite important also, because our lambda over D is not the same as a 6.5 meter telescope. The D is different. And for MIRI, it's kind of a little bit better. You see, it's almost using the full diameter of the telescope. It's especially for the 4-quadrant phase mask. On the other hand, those masks are very sensitive to jitter and pointing accuracy. And so it's in a way, it was a little bit more challenging for MIRI, but all in all, they are very complementary. The inner working angle that we achieve on Sky, I will show some results later, are very similar. It's about, basically, we've been able to image companions, high contrast companions, down 2.3 arcseconds with both coronagraph, pretty much. Even though for NIRCam it's at 4 micron and for MIRI it's at 10 or 11 micron. So this is the way, this is a zoom on MIRI, and the design is from Anthony Vocaletti from Paris Observatory. So you see there's a bunch of real estate in the focal plane, and you can see the cross is slightly tilted with respect to vertical horizontal, I would say. This is what we call the chronograph optical mount. So that's the piece of glass that is not seen by the detector unless we use the chronograph. And that's actually last month in Arizona, I got to see one of those in person. The way it's done, it's basically like micro dots that are on this piece of glass. So I'm not showing the module B, but it's basically the same. And you can see for NIRCam, the way it's done is that the size of the mask. So we designed several masks to adapt to several wavelengths, basically. So in principle, the longer the wavelengths, the bigger the mask for the better attenuation. In practice, we use a lot the intermediate size mask, which is called the 335R for round. We don't use, people at least haven't used that much the small mask and the big mask. The reason for that is the intermediate one has a very interesting, it's an interesting trade-off, basically, to get the highest sensitivity, usually at 444W, the large wave bandwidth filter for planets, yet get a decent inner working angle. And with this mask, we have imaged companions down 2.3 arcseconds. So, but of course, at 0.3 arcseconds, the transmission is something like 10%. And then we have those wedge masks or bar masks. One is for the short wavelengths and one is for the long wavelengths. And those were designed so that you can basically point at different positions depending on the filter you're using, because lambda over d changes with lambda. In practice, it turns out, and I will show some results later, that this has been a little bit more difficult to use, but one position is extremely interesting. It's like this narrow position here has been used, and there is a new paper by William Ballmer showing that you can actually reach also 0.3 arcsecond inner working angle and image planets with that. But the difficulty here, and I will show with the chronograph visibility tool, is that you must design your program so that the object you're trying to image is not in the plane of the bar. And so that means you have to have some constraints in your when you observe and at which aperture position angle, sorry. Those black things here are density filters, and they are used for target acquisition with NIRCam. So a little bit of detail on that. I already explained why we had Leo stops and the fact that they have this kind of weird design. Now I'm going to move to a few science highlights and on Sky capabilities. So the number of papers for chronography, and I have this like library that you can use if you want. It's not that big. It's about 20-25 papers at the moment. And I'm only including here the pure chronographic results, even though in this field, you know, we tend to consider non-chronographic PSF subtraction or even high contrast imaging done with IFUs or aperture masking part of our thing. I have another library for that. But basically, it's not too surprising. Those are modes that are a little bit difficult to deal with. especially with infrared detectors, bad pixels, and also the target acquisition alignment issues. And also our total fraction of time that that is dedicated for coronagraphy is about 3% so far. Might go up a little bit with new surveys, but it's been a really modest use of the telescope so far. I will say that some surveys are ongoing, and Aaron is actually leading a couple of those surveys. One of the biggest results so far has been this new planet detected with MIRI, which is a mature planet, so it's not young and dusty like the planets we were used to do direct imaging of, and it's really cold, and it wasn't also at the position it was expected from astrometry and radial velocities. So this is also pre-launch simulations, and this is just to illustrate the synergy MIRI and NIRCam for circumstellar disks, for example. Basically, we don't have spectroscopy with coronagraphs on board the JWST, but having those filters, it's very complementary with each other, but also with the ground, because the ground you cannot access basically anything between the L and M band. And here you can have all these filters. So this is an example of that synergy. This is the Beta Pictoris system imaged with NIRCam and MIRI. So this the main PR image here, and that's the paper from Isabel Rebollido from last year. The white stuff is completely new. This tail here, which we call the cat's tail, hadn't been seen before, and this is MIRI long wavelengths. You can see that some of this stuff here is also real. So the interpretation is that there was some kind of collision here happening. And the main disk that you see here, the main disk plane, this is the red stuff you can see here. It's mostly NIRCam data at shorter wavelengths. And then simultaneously with the same data set, there's a paper by Jens Kammerer about the planet B, which we could also image. It was not guaranteed before launch that we would be able to basically image planets that close. Turns out it's pretty easy for NIRCam. The planet's pretty bright, and also it was imaged when it was pretty almost at the maximum separation. This is another disk. That's a paper by Kellen Larson. There are actually two papers already with NIRCam coronagraphs by Kellen Larson. This is AU MIC. I'm not going to give too much details, but and Kellen has developed some really nice suite of software to basically work with disk forward modeling and also deconvolution. The convolution with coronagraphs is a very ill-posed problem and difficult because the PSF is spatially varying. So it's not that trivial. This is one of my favorite results with the NIRCam coronagraph. So this is using the bar, and props to William Bolmer, who's a student here at Hopkins, who basically was able to exploit that complicated data set where we basically observed a few systems at this position. So this was kind of a shared risk mode that was done between calibration time and GTO to basically and this was an idea from Marshall Perrin, Laurent Pouet, and other people that were in the coronagraph working group in the past. The idea was basically, regardless of the filter, use that most narrowest position of the long wavelength bar and orient make sure the PA was such that you could see all 4 planets at the same time. So it was a very tricky program. We spent actually a lot of time before launch to simulate this kind of data. But this is basically at the time of observation, the location of the planets with respect to the bar plane and the position. So planet B is pretty ideally located. It's perpendicular and pretty far away. But then you can see that planet C and E are well inside the inner working angle, which is in this case 4 lambda over D. So this is the reduced image, and you can't really see planet E unless you subtract the 3 others. And when you subtract the 3 others, it pops out very well. I must say, this has been done also with the round mask, and we can also see 4 planets with the round mask, but with lesser throughput. And this is from Williams' paper, where they also show the convolution of the planets themselves. So if you deconvolve this, and that's work by Kellen Larson, you can see a dot, because the NIRCam PSF is really strange. It's a bit kind of a flower or a snowflake or something. And you deconvolve it and you get a dot, and then you basically reconvolve it by some kind of Gaussian kernel, and you can see this nice image. And doing this at different filters, the outreach team here made this wonderful image, and that's a real image, even though it's been kind of massaged quite a lot. This is actually one of the main results of that paper, where because of the suite of filters we have with NIRCam, we're able to see that there is probably carbon dioxide in the atmosphere of the planet. Because the flux here drops tremendously between 4.3 and 4.1, 4.05 and 4.3 micron. And that's the main result I was talking about from MIRI. I mean, I said main result, there are tons of results, but this one is very striking because this is the coldest, at this point, this is the coldest and most mature planet ever imaged. And the unfair advantage of MIRI is striking. You can even see diffraction rings around the planet, even though this was basically missed by a very long campaign on the ground with a NIR instrument at the VLT. They can basically barely see it now that they know it's there. This is a slide from Erin Carter, as just to say that basically the whole game is to improve the contrast with, this is the semi-major axis. So JWST is not quite as good as the ground to bring the inner working angle down, but the sensitivity at 4 and 10 and 11 and 15 micron is so good that we will basically detect less massive planets or colder planets or more mature planets. And those are simulations done with the Pancake software, which is kind of an extension to the ETC. This is another slide I'd like to show for performance. This is kind of the record breaking contrast we achieved with NIRCam, and this is at very large separation because this was done with a large mask on a bright star and using the full frame mode. So basically, that's as deep as you can go with a coronagraph with NIRCam. And so it's better than 10⁻⁷, and that's pretty much what was expected from the photon noise and the readout noise. By the way, if you want to find that data set, there is this interface in MAST where you can actually put the object, in this case for Malho. You can select NIRCam, and if you start writing mask here, you can get a pull-down menu where you can select, give me only, for example, the 430R, so the large round mask, and it's not that common, and so that's basically all there is for Malho. And then you can see basically the level 1, 2, 3 of the data, and you can download it, but you can also generate an API query for your notebooks. So I'm going to talk about, so for NIRCam, there was a new, a new capability since basically it's already almost 2 years old, but for a long time, this was in the works. So basically at the beginning, from commissioning to the first year of operation, we were limited to either do short wavelengths or long wavelengths. And since June 2023, by default, everybody gets both. And this is the white dwarf companion that is in my commissioning paper 2022. But in this case, we just let the pipeline do its quick look analysis, and you can easily see, and that's 10 to -4 contrast. So this was just to validate that the whole chain of data management operations, everything was working with this new capability. But of course, when you use this capability, and there is some updated figures in JDocs, in the documentation, you basically always have to favor one of the channels to design your program. And then what you get on the other channel is kind of not as optimized. It's hard to optimize for both. And I must say, most surveys, they use the 444W on the long wavelengths and the 200W filter on the short wavelengths, because those are the most sensitive. So basically, yeah, you have access to almost all the NIRCam filters, not quite all of them. And so for each observation, you get one of these and one of these at the same time. But the mask, there's only one mask in this case. The focal plane is common to both channels. And each channel has their own Leo stop, but with the same geometry. So how does coronagraphy work? In principle, if you have a focus telescope, a flat and stable wavefront, a low jitter, and a good target acquisition, so a good centering of the star, of your mask in front of the star, or the star behind the mask, or whether, then we are game, right? Of course, the chronograph has to be aligned also inside the instrument, so the pupil and the Leo stop, etc. So that seems very simple. We're like, oh, we're in space. We don't have the atmosphere. We don't have turbulence. So in principle, that should be easy. And this is also a pre-launch simulation done by Jaron Leisenring, where basically when the star goes behind the mask, you can see the attenuation in the center, right? But the attenuation is not quite enough to see any companion. So in this case, there are 2 injected companions. To actually see the companions, you also have to subtract the reference star. So the reference star can be a second role, or it can be a reference star for what we call RDI, or reference differential imaging. So when you subtract the reference star, if everything is well aligned and well scaled, then you can see the companion at moderate or high contrast. So that's how it's supposed to work, right? So yeah, little mistake here, little glitch. So this was, by the way, one of the plots of the commissioning paper, where I actually had 3 reference stars instead of 1, and each reference star had a set of 9 small grid dither, like subpixel dither. And what at the time, our target acquisitions or centering was not very repeatable and not as good as what it is now. And so I basically performed PSF subtraction using each individual dither for all 3 stars. And you can clearly see the contrast improving when the reference star was at a position closer to what I considered science star, which was this system with this white dwarf at 0.5 arc seconds. And so, since a couple of years, we've been working on trying to improve the repeatability of the target acquisition, but it's not that easy. But basically, small grid dither allow when they are combined, and also when you use a library of more than one star, if they are contemporaneous, you can basically improve your contrast, especially at short separation. This is Aaron's most, this is basically the ERS result on a real planet that was done just a couple weeks after the white dwarf companion. And that's pretty much the same contrast, but at slightly larger separation. So it was actually it was a perfect, basically, case to check that everything was working with both NIRCam and MIRI. I think you all know that paper by now, at least most people working in this field that are on the call. This is a great result using the MIRI Coronagraph on the HR 8799 planet, same as the Balmer paper, but using MIRI. And as I explained before, even though we are much larger wavelengths, so basically the beam size is much bigger, the MIRI Coronagraph performs so well that you can see the 4 planets simultaneously. So this is really a great result. And on top, that's basically the PSF before subtraction. Okay, so how do you choose your high contrast mode? And so it's been a while already, but we've wrote this high contrast imaging roadmap and a suite of articles on JDocs. JDocs is much better than it used to be for the search capability. So when you basically search something here, you start typing a word, you immediately see popping up all the options of, so if you start writing Coron, for example, you will see all the articles for Coronagraphy. It's pretty convenient. I used to show this plot before launch, trying to explain the parameter space of the aperture masking mode of NIRIs, the NIRCam chronograph, and where the planets will fall. Of course, this is wrong because you know, at different wavelengths, the flux of the planet changes and so on. But that's kind of to give people a sense of what was possible. Also, I think this curve of MIRI should be way closer here because, as I said, we can actually see planet E with MIRI. And that would be the NIRCam imaging without chronograph. And the IFU is also, there's a paper by JB Rufio showing that you can actually achieve a smaller inner working angle with a near-spec IFU than with NIRCam. This is also Web PSF pre-launch, and that was in the Parents 2018 paper. It's just to explain the strategy, and what limits us here is basically the photon noise at large separation. You have to know also that with the NIRCam chronograph, we are only using 19% of the light, and so let's say our signal to background or signal to noise floor ratio is not as good as with imaging at large separation, which means that NIRCam chronography and MIRI chronography are very niche. They are really designed to do small inner working angle, so to work at small separation or at slightly larger separation, let's say a few arc seconds, but around very bright stars that would otherwise saturate a lot the detectors. Something to say here: the exposure time calculator doesn't have target acquisition error or small grid jitter implemented, and so what you get from the ETC when you subtract a PSF is very ideal, but you can basically almost recover the performances of the ETC if you do everything right. If you follow the recommended strategy of using a small grid jitter and a good reference star, and you also perform principal component analysis or clip subtraction with spaceKLIP, you can basically almost recover what the ETC gives you, at least, let's say, down to 0.5, 0.6 arc second. This is a paper by Jens Kammerer that was done slightly after commissioning, also on the commissioning data sets, comparing the contrast achieved at that time between coronagraphy and aperture masking with NIRIs. So you can clearly see that for some angles at moderate contrast, aperture masking is better, but that's even more niche, I would say. So an outstanding MIRI issue is the glow stick, but basically this glow stick that's you can see here, the more, the longer the wavelengths, the more it glows. This is something that has forced us to recommend people to take dedicated background for each observation. And MIRI chronograph works beautifully, but because of this background strategy, it's kind of time consuming to do observations. But, it's better to use the time, to take the time, but do a very good science case than not. For surveys, it can be a little bit prohibitive. So NIRCam problems, I'm going to say a little bit more because I know a little bit more about it. So the contrast fundamental limits, they were, pre-launch, they were curves that were keep on going down that were published, especially in the Beischmann et al. 2010, for example. Since then, we know that, what limits us is really the background and or the readout noise. And so Nicolas Godoy has done this SPIE paper where he shows basically what limits you for several data sets. Comparing, he does Monte Carlo simulations and try to reproduce each part of the contrast curve. In general, I would say if you want to gain at small angles, you need to do a very good strategy. So the strategy can be small grid dither. You have to be lucky also that your target acquisition between your star and your reference star is actually very close. And to gain, and then you have to be aggressive, for example, by using a library of more than one star, so you can push a little bit the principal components and clean up this inner 1 arc second of NIRCam, which is very speckle dominated. At long separation, if you really want a deep detection limit, you probably have to go for the larger mask. And also integrate longer and maybe go full frame. So this is another illustration of the commissioning data set where I showed the different positions. So this was our target performance at the time. Our specification, and this was just for the round mask, intermediate round mask, was to basically land the star at within 0.5 pixel long wavelength pixels, so about 30 milliarc seconds. And we almost achieved it straight away during commissioning, but in some case, maybe 2-3 sigma cases, the stars landed a bit further away. So basically, the small grid dither implementation, and shout out to Rémi Soumer and Laurent Pouéot, who worked a lot on that in the past. The small grid dither strategy has saved us in recovering basically the contrast associated with the principal component clip subtraction method. Why is it so difficult to do target acquisition with NIRCam? It's a combination of things, but we basically don't ever see this image on sky. Basically, we don't see the mask. This is a ground image. And basically we have our telescope pointing, then we do a first sense reading to go on this stamp image, which can be either clear or behind a density filter for bright stars. And then we do an offset, which is about 10-12 arc seconds. And that offset has to be perfect to place the star here. So the central reading has to be perfect, and that's an old, it's an old system with a center of gravity with bad pixels and so on. And then we do this offset that is heavily depending on the distortion model that we can only measure when everything is in place, basically. So basically, that's why we are not, that's why it's not trivial basically to achieve, let's say, less than a 10 milliarc-second precision. So this is work done by generalized learning, where it's trying to like evaluate. This is already a little bit old plot, but like for different masks and target acquisition, what's causing the error, and what's the distribution of landing positions. By the way, we are much better now. I think we let's say our 1 sigma is around 10 milliarc-seconds and our 3 sigma is around 30. It's not moving on. Okay. Yeah, and that's just an improvement we've done. It's a slight improvement. We basically changed the size of the box that we do the centroiding on, and the centroiding was very skewed in X because of the non-central symmetric core of the PSF, and we basically gained a little bit. Another thing I'm working on since a while now is actually to improve the distortion model. You may have, if you already used on-sky data, you may have noticed that the WCS is not correct for coronagraphy, and the distortion model is okay, but we have basically 5 to 10 milliarc-seconds distortion residuals in the chronographic area where our subarrays for chronography are. So I'm trying to do a better job so that soon, in principle, we'll have a better WCS and distortion. And now we have basically a target acquisition which is performing a 3-point dither. Basically, we lost a little bit, a small fraction of the time. There were failures of target acquisition due to new bad pixels that were coming in the target acquisition subarray. You have to know that, you know, the way it's been done is that once in a while only you change some kind of bad pixel map and flat. It was not often enough, basically, so some acquisition failed. And now we are doing a 3-point dither, and it's taking a little bit longer, a few minutes, but it's much more robust. So as a conclusion, chronography in space is actually quite difficult, especially when the whole system was designed a long time ago and you don't really have access to real-time or software changes that are agile, I would say. So we still have some issues with the astrometry, I would say, but it doesn't prevent people to publish their relative astrometry, and it's been done, and that's mostly what's done in high contrast imaging. And in general, this is what we do here, is we try to maximize the science outcome for you guys. Optimize the intrinsic data quality, monitor and characterize performance, fine-tune the calibration. We actually updated the photometry 0 points. They're pretty good now for NIRCam, I think for MIRI as well. Try to always ease the use basically of the whole observatory from the scientific ID to the design of the program to the observations to the data reduction. And there's this data to paper initiative, and that's why we also have some notebooks that are available for people to try. And then we also try to improve efficiency, expand capabilities, etc. But this takes time because it's a large mission. Any technical time we do is in competition with basically the community's science time.